Good morning and welcome you all to this next lecture on the inorganic chemistry of life perspectives principles. In the previous class we have been looking at a few aspects. I will bring recapitulation of those. One of that is we looked at absorption of elements by intestine, and this we have looked at as an example for the iron case. Then later on we also looked at the inter element absorptions will have interactions either antagonistically or synergistically. So, antagonistically is that when the concentration of one of the element goes up, the concentration of the other element would get hampered. Synergistic is exactly reverse to this, where the absorption of one of the element will favor the absorption of the other element as well. This is all we have seen. Further we have looked at another aspect, how these metal ions are bound in biological systems, in particular to proteins. In that we have looked at it is the side chains of the amino acids, and we have looked at there are certain side chains like carboxylic, like amine, like thiol function, such as aspartic glutamic, histidine, cysteine, serine, threonine, all these kinds of amino acids having side chain ligating centers which are capable of binding to the metal center. I have also talked to you there are some special factors like heme. Heme is nothing but the porphyrin containing iron center. So, this entire heme is again embedded into the protein. So, therefore, the metal ions are directly connected to the side chains of the amino acids of the protein, or they are present in heme like systems or porphyrin like systems, and porphyrin like systems can also have additionally coordinated to the protein, where 5th and 6th coordinations are still available because the heme provides only 4 coordination, and most of the transition metal ions, particularly the iron, nickel, these kind of cobalt ions can extend their coordinations to 5 and 6 as well. So, therefore, the metal ions are bound either to the amino acid side chains or to special compartment or a combination of these, and this is what we have learned in the previous class. Now, let us look at the same with the example being given over here. So, this is a protein which is nothing but which I explained to you called transferrin. A transferrin, as I said earlier, transports the ions across the blood, from one organ to the body to the other organ via the blood. Now, you see that. So, you have an iron center, and iron center is covered by the protein, and if you expand this region you could see the whole thing here. So, what are you able to see? You have a metal ion center which is the iron, which is connected to this which is the phenolic oxygen, another phenolic oxygen. So, where does the phenolic oxygen come in kind of a amino acid side chains? It is the tyrosine. So, the tyrosine gives you the phenolic group, and the phenolic group upon deprotonation becomes phenolate, and this phenolate will bind over there. So, you have two of them are tyrosine groups, tyrosinates, and then one of them is nothing but the nitrogen of the imidazole moiety, which is coming from the histidine. So, therefore, it is a histidine binding. The fourth one is a oxygen or the carboxylic, it is a CO and there is another O, and this is coming from the aspartic. So, you could see here there are 3 different types of amino acid residues, totally 4 such residues are binding to give a 4 coordinated species, and we know in case of iron with the 4 coordinated they are very likely to be of the tetrahedral type, but I will come to the geometry aspects bit later stage. So, you can see therefore, the iron ion in enzyme like transferrin has a coordination sphere, and if you take this just this portion alone, it is a primary coordination. So, it is like an iron is suspended into protein in the form of a complex, where the ligands are the side chains of the protein. I hope you understand this. So, to make your understanding further better, I will show you one more example. This is an example of an enzyme where we have a plastocyanin. So, right now you do not need to worry what this enzyme is, what its function is, though its function is electron transfer. It has two types of metal centers, one is the copper center, other is the zinc center. Okay. So, zinc center, copper center. So, you have a copper center, zinc center. So, these are different subunits. So, do not bother about all that. So, if you look at the corresponding case of this particular metal center, which is the copper. So, now you can see that the copper is surrounded by 4 ligands. Okay. One of it is cysteine, this one is cysteine, sulfur, and this is cysteine sulfur, but it is not cysteine, it is a modified cysteine. Modified cysteine is SME. So, SME is called the methionine. Okay. So, therefore, is a methionine. So, methionine sulfur, which is a ether, thioether, and then this is a cysteinyl sulfur, which is S minus. So, this is S minus is SME, and then you have a histidine, which is you see from the perpendicular view. So, therefore, you are not seeing the total plane. You can see another histidine here, which is you can see the nitrogen. So, in this case there are 3 types of amino acid residues, one is histidine, other is cysteine, other is methionine. Okay. So, but there are totally 4. The 4 amino acid residues are bound to this. Now, what you can call this as this is a coordination complex. Now, and these amino acids are connected to the protein, therefore, it is suspended in a protein. So, therefore, the metal ion copper here is suspended in protein through the bindings of these. On the other hand, if you come to zinc center, you can see here zinc has got in this particular case the 3 bindings. 2 of these are from a carboxylate. You can see it is a carboxylic group, it is a carboxylic group, and one of it is the imidazole, which is a histidine. There is a tri-coordinated zinc center that you have and a tetra-coordinated copper center you have. Later on you will learn that the copper center is the actually the one which is reaction center, and the center of the zinc is basically the one which stabilizes the structure. So, stabilizing the structure, so it is not involved in the function. So, therefore, this is structural ion and this is the catalytic ion. I will bring this distinction a bit later, much more clearer. Right now you can say non-functional zinc, a functional copper. So, the copper is involved in the redox process of the transferring the electron back and forth. Okay. So, therefore, redox enzymes. Okay, having seen these 2 examples, let us have a bit of survey among the large number of proteins, of which I have picked up a few which are zinc containing and maybe the iron, maybe the copper. Let us first look at this particular table, shows different enzymes based on the zinc. Okay, so it may be useful for you if I take you through this even in a later stage, because you can study better in future when you look at the books, etc. This enzyme name is carboxy peptidase and it has a lot of protein which is not shown here, but what is shown here is a zinc center. Zinc center having one histidine, another histidine, another aspartic, and there is a water. And so, and in this case the aspartic having a carboxylate group, it binds like a bidentate. So, therefore, 2 coordinations from this, 1 coordination from this histidine, 1 coordination from this histidine, totally 4, and 1 more is the water. So, I will explain you why water is there, what water does, everything when we come to this enzyme thing. So, right now your idea is to take that in this particular carboxy peptidase, the zinc center has got the binding from these different amino acids coming from the protein and forming a 5 coordinated structure over here. And there is another example just below this. This has got not one zinc center, but this has got two zinc centers. You can see that two zinc centers, zinc 1, zinc 2, and similarly this is also bound by a histidine and aspartic, also by histidine, aspartic, and there is a bridging ligand. The two metal ions are bridged by another aspartic carboxylate group, and there is one more bridging which is coming from the water. Okay. So, therefore, the two metal ions are not separated, but bound together or bridged together by an aspartic and water molecule, and each of this is a coordination sphere. Now, that means this di-zinc center is suspended in a protein called amine peptidase and it functions. We will see functional aspects at a later stage. May not be for this enzyme, but some other enzyme too. Another example you take, the enzyme's name is carbonic anhydrase. Carbonic anhydrase, you have one histidine, another histidine, another histidine and a water. So, there are 3 histidine residues bound through the nitrogen, and which is nothing but from the imidazole moiety. So, you know the imidazole moiety is a 5-membered ring having a nitrogen which has a lone pair which will bind to the metal center, that is what, and then you have one water, role of water, etc., we will be seeing later. So, now what you can see, this zinc, this 4 coordinated zinc is a coordination complex which is suspended in a protein. Then you have another example over here, astaxin and thermolysin, again zinc having a 5 coordinated structure here, as you can see, and similarly you have on this side on the top alcohol dehydrogenase. We will be studying more details about this enzyme, about their functional etc., to much later stage when we come to the story of the zinc enzymes. This has a different kind of amino acid residues. What are those residues? You have a cysteine, you have a cysteine. What is cysteine? Cysteine has a CH2SH. In the CH2SH, the proton is lost, the S minus. So, it is a thiolato. So, it is a thiolato bond, zinc thiolato, zinc with the S cysteine, zinc with the S cysteine and zinc with the histidine. So, there are 3 amino acid residues, the 4th one is water. Okay. So, therefore, a zinc coordination complex is suspended in an enzyme called alcohol dehydrogenase and does its function. So, come to another example, alcohol dehydrogenase also has, this is the same example, but it has 2 metal centers. One metal center I explained to you here, this is a catalytic center, that means reaction occurs here, and there is another zinc center which is structural, means no function occurs at this place, but it is required. It is required because it has to hold a particular kind of a conformation structure. So, you call it as a structural rigidity. So, structural rigidity for the protein is obtained when the zinc, this kind of a zinc is present. And what is this zinc? This zinc is bound to 4 cysteine things, different from the zinc that is here. So, you have a 2 distinct zinc centers, one is the zinc catalytic center and the zinc structural center, both of these are there. Okay, both are a part of the same protein, but 2 different centers. So, more details will come when I explain to you the alcohol dehydrogenase, its function etc. And there is some proteins called zinc fingers. So, in the zinc fingers you have 2 histidines and 2 cysteines. And leucine, there is another example, leucine aminopeptidase. Okay, this has got again 2 zinc centers, and each of these is bonded by the aspartic, again one histidine, one aspartic, and these are bridged by the glutamic and aspartic carboxylates and with one water or hydroxo species. So, these are the kinds of things. So, what do we learn out of this entire table of things is that there are variety of zinc enzymes are there. Each of the zinc enzyme has a different function which we are not learned right now, which we will be learning later stage, but we know that they have different enzyme, different functions, but they have a different coordination sphere. And a common feature is in all the cases zinc ion is suspended in the protein and bonded through amino acid residues, side chains of the amino acid residues, and in some cases water molecule. And in some other cases not one zinc, it could be 2 zinc di-zinc center, and both the zinc centers may be bonded together or bridged together, and this is what we understand from this particular table. It is nothing too special with the zinc proteins. Let us look at a different kind of proteins based on the copper. So, let us look at the copper based enzymes. So, again I have given a table of this. So, I will not go as detailed as I have gone in the previous slide, I will go a bit more quickly here. So, what do we have here? There is one protein called plastocyanin, there is another protein called galactose oxidase, there is another protein called azurin, there is another protein called oxyhemocyanin, there is another protein called copper zinc superoxide dismutase and cytochrome C oxidase, okay, and blue copper sites which are perturbed. I will explain you at a very later stage why the meaning of perturbed is coming into, but give you a small hint right now. And then we have other kinds of axially substituted blue copper sites, etc. In fact, the plastocyanin, that is one, the azurin the second, and the perturbed blue copper sites third, and the axially substituted blue copper sites. These are all coming from one particular class of copper enzymes, and these particular class of copper enzymes are known as the electron transfer blue copper proteins. So, they are blue in color, therefore, they are called the blue copper proteins. Okay. So, all of these four have the same function, which is electron transfer, but other enzymes have a different function. So, for example, galactose oxidase, it will oxidize the galactose, primary hydroxyl of the galactose, okay. And oxohemocyanin, this is involved in transporting the oxygen, not in human, in molluscus. I will explain later when we come to the story of oxygen transport. And the copper zinc superoxide dismutase, in this case the superoxide radicals are dismuted, O2 minus are dismuted. This also I have already mentioned earlier, nothing new, but details will come later on. And this is a cytochrome C, this supports the heme center. So, therefore, that much we will see at this stage in the electron transfer process. And this again I told you, this is electron transfer protein, this is also electron transfer protein. So, now what have we studied from all these this entire table? We have variety of copper containing enzymes. In each of the case that the bound residues are different geometries also are there, 4 coordinated, 5 coordinated, so many things are there, and they all do different functions. That means a copper ions are suspended in corresponding protein, bonded through the different residues of the protein and making into a copper enzyme. And if this much information is understood, this much information is assimilated by you regarding this one, as absolutely more than sufficient at this stage regarding the metalloproteins and metalloenzymes. I will show another table which is pertinent to the ion enzymes. So, first of all I have to tell you, when it comes to the ion enzymes, I have to tell you there are two types of ion enzymes there. One is the ion enzymes where ions are directly bonded to the side chains or the amino acid residues. The second kinds of ion enzymes where the ion is bonded to a unit which I have already introduced to you, is called the heme. So, there are the 4 nitrogens of the porphyrin are bonded to the ion. So, therefore, these are ion nitrogen bonds, and this in turn is bonded to the protein. And remember, there is the ion in this hemes has got only 4 coordination, and the 4 coordination in more or less in a square planar fashion. So, iron is capable of showing 5th and 6th also, that means 6 coordination. Therefore, the 5th on the top, 6th on the bottom, these are vacant. So, either both of these or one of these can be bonded by the side chain residue too. So, therefore, there are a huge range of heme proteins are there. So, in this case what I am telling you, in case of iron there are 2 major classes of enzymes. One class of enzyme is called the heme enzymes, and the other class of enzymes are called the non-heme enzymes. In case of non-heme enzymes, the iron is directly bonded to the amino acid residues, okay, side chains of the amino acid residues. You can see here rubridoxin, and you can see ribonucleotide reductase, you can see aconitase, you can see methane monooxygenase, you can see 4 iron 4 sulfur cluster, and extradiol dioxygenase, and you can see superoxide dismutase, so many things. In all these cases, many more are there, but I am giving only a few selected examples just to give a feel. In all these things, the iron is suspended in the protein, and where the iron center is bonded by all these side chains of the amino acid residues. In this case, it is the cysteine. In this case, for example, aspartic carboxylate, this is glutamic carboxylate, this is histidine, okay, and this is bridging glutamic, and these are waters. The role of water we will see at a bit later stage. There is a lot of important issue with the water presence there, because they are involved in the catalysis of it, or they are involved in allowing the substrate to be bound to this. Okay, so I have been telling you about the different types of iron enzymes, heme and non-heme, having different residues bonded to that, and in case of heme, 4 coordinations are filled by the porphyrin, and 2 other coordinations are in one of these coordination is bonded by the protein. When only 5th coordination is bonded by the protein, 6th will have most of the times as a water, and this can provide a substrate binding as well. So, as I said, the water position have got 2 kinds of roles. One, it will be sort of a ligand where can be exchanged by the substrate. The second case is where the water is involved in the reactivity. So, these are 2 possible ways that we can see. So, what all we have seen till now in the metalloproteins and metalloenzymes. In the metalloproteins and metalloenzymes, the metal ion is suspended in the protein, not just like that, but it is bonded to the side chains of the amino acid residues, or it is bonded to a special group like heme. So, therefore, heme bound things. When the heme is bound, there is a possibility the 5th and 6th coordinations can be bonded by the protein, or even 5th coordination can be bound by the protein, and then in such a kind of a thing will basically function. So, now what do we understand from a metalloprotein or metalloenzyme? So, metalloprotein or metalloenzyme is metalloprotein or metalloenzyme is you have a protein plus metal ion center, which is coordinated to the protein. So, therefore, one can basically see this as, so the metalloenzyme is you have a metal ion complex plus the protein. So, in other words, we can say any of the metalloprotein or metalloenzyme where you have a metal ion bonded to the protein as like a any other coordination complex, and this coordination complex is held by the protein. So, what do you think such a kind of a complex can do? Let us at this stage itself, let me bring to you a simple case of, let us say I have an iron salt. Okay. So, I have iron salt, let us say iron 2 plus salt, let me put in water. So, therefore, I get FeOH 2 plus complex. Okay. So, now if I put this iron in the protein, iron 2 plus protein. So, I will have a metalloprotein where the metal center is coordinated to the protein. There are two things are there. So, one is that direct binding of the protein resulting in a coordination complex. So, this complex is not a simple innocent kind of a complex like what you have in water. So, in water you have just simple iron water aqua complex. In case of the metalloprotein, the iron 2 plus bonded to the protein and the protein structure and the protein conformation, all these will influence the properties of the iron center. Therefore, what I want to convey to you is that the properties of the iron ion in iron aqua complex is absolutely different from the same iron ion when it is bonded to a protein and when it is bonded to different kinds of proteins. So, therefore, diverse functions, diverse properties are possible by the same iron ion, but in different media. So, therefore, in case of test tube reaction, the water is the medium. In case of the metalloprotein and metalloenzyme, it is the protein which is the medium. So, therefore, medium played role on the metal center is very influential. So, in one case it is water, in the other case it is the protein. So, the protein binds to this and protein alters the functions and protein takes care of the modifying the functions of all of these. So, that is very absolutely interesting. You know why it is interesting? It is interesting because you have seen there are hundreds of different types of metalloproteins and metalloenzymes even for iron. If each protein does not bring such a change, then all proteins should have behaved the same way, but they are not true. Each of the enzyme have one different function. Whether it is a zinc enzyme, there are 100 different zinc enzymes are there, in fact more than 200 are there, and there are several hundreds of iron enzymes are there and several dozens of to 100 of copper enzymes are there. In each of these the coordination is different. Some cases coordination very close by, but the protein is different. So, it is because the protein is different, the properties imparted to the metal center do differ. So, therefore, protein plays a very important role. Simple copper aqueous solution or copper amine complex and a copper in the protein. So, protein will also have nitrogen ligands. So, therefore, we cannot say that the copper present in a protein will have the same properties of the copper ammonia complex. Similarly, iron, so iron aqua complex. So, we should not think the simple iron aqua complex which is present in test tube, its properties are going to be the same as the properties of the iron 2 plus in a protein. It is absolutely different. In each of this protein and enzyme, we have a different kinds of properties there. So, therefore, the proteins modify the properties of the iron or zinc or copper, thereby we have nature has evolved with a huge number of different kinds of enzymes. That is the take home lesson that one should see. And just before we close this particular part of the thing, I would like to tell you that these are already I have talked to you that they are bonded, and this table will give you that different bindings, binding in case of potassium, magnesium, calcium, etc., manganese, iron 2, iron 3, copper, cobalt, nickel, copper 2, copper 1, all these kinds of things. So, you have a different kinds of the binding, and the reasons for this binding I will explain you later, which is can be explained based on the stability and also based on the HSAB, hard soft acid base concept at a bit later stage. And so, whatever I have talked to you is about there are different essential enzymes, you require specific dosage of these per day and they have certain functions. So, different kinds of functions are there for each of these, the manganese, vanadium, iron, cobalt, etc. In all these things they have different kinds of functions. Some of them may be showing only the carrier osmotic pressure. I will come to this a little bit more a bit later stage on this. So, to sum up, let me tell the following. So, we have seen that the metal ion is bonded to the side chains or the amino acid residues of the proteins, and these amino acid residues of the proteins bind and make a complex. So, therefore, it is like a metal ion complex is suspended in a protein, and the properties of such a complex is different from the properties of simple complexes that we see day to day or we see in the test tube, because the protein applies its own parameters of the conformation and other hydrophilic properties, etc. As a result of that, the metal ion center properties are changed dramatically, therefore, different enzymes function differently, though the coordination sphere may have very close by. Thank you very much.